Hi everyone, I'm Melissa Illingworth and this is my video about finding the pH of a buffer. So for this example, there's two different solutions that are combined. Just gonna highlight them. And here's the other. And it says that they make a buffer, they will, and we need to use the Henderson-Hasselbalch equation to eventually find the pH of that buffer. So I've included that here. So we have two different places for our solutions. We need to find which is the conjugate base and which is the weak acid. So the weak acid, which is abbreviated commonly as HA, it's the one that's going to be an acid. It's going to be giving up a hydrogen. It's the one that has more hydrogens. And of our two different compounds here, there's only one that has any hydrogens at all. So for us, it's going to be the Na2HPO4 as our weak acid. The conjugate base, which is abbreviated A-1. That will be whichever one that has less hydrogens, which in our case is our other Na3PO4. So we've identified what's going to go where, what's going to be our weak acid and conjugate base. Eventually we'll find those concentrations to plug into the Henderson-Hasselbalch equation. The next thing I like to do is to find the pKa. So what are we finding the pKa of? It's the pKa of the weak acid. So we already know that weak acid, Na2HPO4. And for this, we'll need a table of some information of the weak acid Ka or pKa values. And when you look at any table like this, you won't see Na2HPO4, but you'll find something that's close. You'll see this, HPO4 minus 2. So in our question, we've just completed that as to having the sodiums there to neutralize the charge so that we have an even amount of positive and negative charges there. So this is the weak acid, though, of our solution, and that's what we need to find the information about. And so I have a table with its Ka values, and that Ka is 4.2 times 10 to the negative 13. So we need to use this to find the pKa, and that is the negative log of the Ka. And that is 12.38. So the next thing we need to do is find the pH. So to complete plugging in everything to the Henderson-Hasselbalch equation, we need to find the concentrations. Of the weak acid and the conjugate base. And for that, we're going to use this equation, M1B1 equals M2B2. So just to flip back to our pieces of information, I'll start off first with the conjugate base right here. We have 50 milliliters of it, and its concentration is a 0.6 molar. So we have its M1 is 0.6 molar, and we have 50 milliliters. We're going to find its new concentration, its new molarity, M2. And then for the V2, we need that to be the total volume. So we're combining 50 and 35. So that's going to be 85 total. So our A-1, our conjugate base concentration is 0.353 molar. And we need to do the same for our weak acid. The Na2HPO4. And for that one, its concentration was 0.7 molar. And we had 35 milliliters of it. We find its new molarity. And again, we need that total volume when we combine the two things, 85 milliliters. So our HA concentration is 0.288. Now we're going to use these and plug everything into that Henderson-Hasselbalch equation. So the first thing we need is that pKa we found, 12.38. And then on top is our conjugate base concentration, and that was 0.353 molar. And then in the denominator is our weak acid, 0.288 molar. And we do need to do this division before we take the log. And when we solve for the pH, we get 12.47. All right, thanks for watching.